Welcome, everyone. My name is Michael Dunn O'Connor. I'm a developer advocate here at Modular, and I'm thrilled to be able to introduce our series of speakers tonight. Before we get into it, I'd like to have a quick show of hands. Who here is in the Modular offices for the first time? A lot of folks, welcome, welcome. And who is already working with, experimenting with, or contributing to Mojo or Max? A lot of folks here also. So we love to see that. We've got a great mix of newcomers and people already deep in the trenches. Tonight's talks are all about the Max framework. This is an AI framework that's redesigning how we build, optimize, and deploy AI workloads. I'm really excited to introduce our series of speakers. We will have a series of talks, a Q&A after each portion, and then we'll stick around and we'll answer questions, have conversations, and of course have more food and drink at the end. So please do stay till the end of our presentation. Our first speaker is going to be our CEO, Chris Lattner. He's going to talk you through the vision for the Max framework. There's a big picture view of where Max is headed and why that matters. Next up, you're going to hear from Faris Boulala, who's going to tell you about Max's graph compiler internals. This is a deep dive into how we balance the need for state-of-the-art performance with the ever-changing requirements of AI engineers. Next up, you'll hear from Ahsan Kermani. He's going to walk you through our new Max API and talk you through how you would transition from PyTorch to Max. This is a live workshop. He's going to share his notebook. He's going to talk you through how you use this API and demonstrate how it makes model development both really clean and very intuitive. Finally, I'll have a short presentation myself, talking you through how do you build an LLM in Max from scratch. This is a tutorial series we developed using that same eager model API that Ahsan is going to present. It's my goal to demystify LLMs and show you that with the right tools, this can be a very accessible technology. Without further ado, please welcome me and join me in welcoming our CEO, Chris Lattner, to share Reintroducing Max.
Thank you, Michael. I'm here to drink Diet Coke for you. Maybe teach you some more things too. Welcome, everyone. Happy holidays. It's really great to see you all. I'm very excited to help to share kind of this next step in the evolution of the software we're building. It's all been public, but it's getting to the point where it's really quite fun and quite interesting. And so what is this Max thing? I think that now people have kind of understood what Mojo is, but Max is less well understood. And we've been kind of, as we're building it, cautious to not oversell. So before we dive into that, I'm going to kind of frame. I think many of you know what we're about, but in case you're not aware of what Modular's doing, today, if you look at the modern AI stack that we all use, it's actually really cool, but it's also really complicated. Turns out that lots and lots and lots of people are working on AI today. Shocking. You've heard this, right? So many people, so many companies, so much innovation, so much stuff going on. It's exciting, but it also leads to kind of a hot mess. There's all this stuff up and down the stack, different serving frameworks, different APIs, different ways to program GPUs, different ways to do hosting. You could argue that Modular is contributing to this problem, right? I mean, if there's 50 standards, having 51 to go unify them all. But there's a reason that we're doing this, right? And the reason is that we want to democratize AI. We want to democratize compute. Our mission is really to bring developers to the flops. Take all these flops, all this innovation. We believe that at the end of Moore's Law, hardware is only going to get wackier and more cool and more exciting. And yes, today's well-known GPUs are amazing, and we want to provide access to them. But as we proceed, we want to really rethink the software fundamentals, really break down the barriers, and get more people into this ecosystem. Because right now, it feels like only the biggest players in the world are able to do the fundamental work. And we think that's backwards. We think the innovation comes from the little guys, the people that are closest to the applications, the people that are pushing the boundaries, the people that are the hungriest. And they may not have $15 million to go train an LLM. So if you're curious, I've written some blog posts. I need to get to writing the next one, maybe over the holidays or something. But we've spent a lot of time talking about Mojo. Mojo is a good thing. I'm very excited about it. We've talked about that a number of times, and it's a really good way to unify GPU programming and other accelerators. But AI is more than just GPU kernels, right? AI is a much more complicated thing. You get modeling, so notably with PyTorch. I assume some people have used PyTorch here. If you want to use it in production, suddenly you care about performance. And so there's a whole bunch of different ways to get performance, a lot of MLR things, Triton, CUDA, lots of different ways to get performance, C++, Rust, lots and lots of things in this. But we need, AI is not itself useful in production unless it's fast. And finally, you actually need to serve this. A lot of data center workloads in particular need to be served. It turns out that when you get into this, you get into the complexity of serving lots of different users, and suddenly the problems compound. You get disaggregated workloads. You get a lot of problems that don't exist with just AI being a forward pass like it used to be 6 years ago. So what we've learned as we leaned into this is we said, hey, well, we're going to build this Mojo thing. We're going to build this cool way to get performance out of GPUs. Let's go use PyTorch. Well, PyTorch is a good thing. I think many people love PyTorch. I love PyTorch. But PyTorch wasn't really designed for Gen AI. It wasn't really designed for inference. And I think the world has also figured this out, right? I think we're not unique in noticing this. We've seen tools like VLLM and SGLang and many other tools kind of come in and try to help PyTorch, because fundamentally what PyTorch was designed for was for traditional AI. It was designed for model training. It's super important. But today's inference workloads are actually quite different. They're only getting more complicated. Getting the host and the accelerator to work together, super important. And things like PyTorch were not really designed for that kind of a world. As you lean into this further, and now you start caring about hardware, you start to realize tools and technologies like SGLang and VLLM, while they're awesome, they also are really just a gigantic bag of custom kernels. If they're a gigantic bag of custom kernels, well, generally they get built for the industry-leading hardware. And then if you try to bring up a new chip, you try to integrate with anybody else, suddenly you run into this challenge of, well, okay, I can implement VLLM, but step one, rewrite all of the kernels for all of the models. And wait a second, this is not a reusable framework. This is a very useful tool, of course, but it wasn't really designed for this modern era. So, we've been working on this for quite some time, and we've been working on the different bits and pieces, and innovating in the space is very complicated. But so today we're excited to introduce and reintroduce the Max framework. And so this is a fully new Gen AI native AI modeling and serving framework, and it's built from the first principles for the modern world. Now, Max framework being built from the ground up, a lot of us have worked on a lot of these different systems. We're paying attention to all the cool research papers. We're seeing all the innovation that's happening. And we have the opportunity to build a next generation system. And so when you have the opportunity to build a next generation system, well, first of all, you can bring the best ideas from everywhere. We're shameless. We'll take good ideas wherever they come, right? But I also feel a burden of responsibility, because if you're going to do this, you should do it well. You should think about the implications. You should try things. And when you make a mistake, and we have, you should take a step back and fix it, right? You should be really deliberate about building a large-scale system. And so with Max, you've got all the performance of graphs, because graphs are a great way to get high-performance systems going, and it's really important for particularly modern workloads. We want it to be easy to use. We want to provide lots of models. We want to have an amazing graph compiler. We want to make it easy to learn and for people to build into this ecosystem. Turns out one of the best things about PyTorch is eager mode. That's amazing for exploration and discovery. And so you need a world-class eager mode. Also, the performance of graphs, right? We want it to be portable, of course. We want to take advantage of Mojo, because I don't know, I think the Mojo is pretty cool. And what we won't talk about today is that none of this technology is actually specific to Gen AI. This is where a lot of the pain is, and this is what we can use to justify building these tools. But if you want to do quantum computing or biochemistry or digital signal processing or anything else totally wacky and crazy, it's all about pushing around a huge amount of data and building and orchestrating compute. And these tools and these techniques should be native and should be able to work for that, even though it's not Modular's focus. So today, as Michael introduced, we're going to be talking and pulling back the covers on state-of-the-art graph compiler. And Ferris will nerd out about MLR internals and other cool stuff like this. And we'll learn how easy it is to program LLMs. And we'll talk about eager mode and how we're going to push the state-of-the-art of the world forward here. I'm really excited about the deep dive talks we have later today. And so if you look, so today, Max covers this full spectrum. You can design and build models, which we'll talk about. You can get good performance, which we'll talk about. One thing we're not going to talk about today is serving, because we didn't have time, but we'll focus on the first two, and we can talk about the third one some other time. So one of the other cool things about Max is it's pervasively open source. And so if you go dive into our repository, you can see lots of different models, and there's more all the time. This is something we're continuing to invest in. We're building it out. We're working with a lot of design partners and customers on this, which is cool. We'll have more announcements later. You can find lots of kernels. And so I think we have the world's largest open source portable kernel library across NVIDIA, AMD, and now starting to turn on Apple, which is also really exciting and cool. We've got the serving components, which we don't have time to talk about today, but they're all public. You can go check it out. And so make it super easy to build and distribute servers. And so we're tackling this whole stack. And so one of the things we believe in is making this accessible. And so, yeah, you can pip install it. You can use Conda. You can do all the favorite tools, make it really easy to get up and running. And we want to make this super fast and easy. And we'll show that later. And so as you dive into this, again, like your curiosity is the only limitation to what you can do. And you can dive into the Mojo standard library or dive into kernels or modeling APIs. And we've also said, of course, we're open sourcing Mojo next year as well. And so this is all part of our big plan to like build into this and really push this entire ecosystem forward, because we know the stakes are high. We know this is really important. We want to do, and we feel a great responsibility to do this well. So that's my part. I think this is a really exciting time. I think the AI is so critical and important to everything we do. I want us to be pushing this forward. I want us to be relentless. I want us to be challenging the state of the art. I want us to be pulling in the best ideas from wherever they are. And so I think Ferris gets to kick things off. Actually, we'll do Q&A first, so you're safe. But to talk about the graph compiler and then dive in. So if anybody has any questions, I'm happy to take them. I think that you should get to the people that actually have technical content to share. So Ferris, yeah, go for it. Yeah.
Oh, thank you. I'm new to the entire Mojo ecosystem, and a burning question for me is, how's the support for the Windows environment?
Windows is one of the things I'm sad we don't have great support. We do support WSL, and so that exists. And so Mojo fully supports that, and you can totally use that. We haven't had time to invest as much as I'd like into that. If you'd like, please do bug us about that, and we can talk about it later.
I would definitely bug you about it.
Yes.
I feel like that's a very important missing piece in the industry.
Yep, I agree.
So this is actually complete news to me. Like, I actually thought Modular was just like building an acceleration layer. And just seeing that it's much, much bigger than that. This event is great to get the news out, but the news needs to be out a lot more.
Yeah, well, so you're surprised we're building also an entirely new AI framework. There's a reason we haven't been talking too much about it. Right. So first of all, it's only now just becoming real. Right. We've been building the components and we've been using it. We've been talking about performance and results and deliverables end to end with this, and it's been very important. But I think now, January, like we're coming together, it's like getting actually pretty good. Now we're not doing training. So people will say, oh, okay, well, I'm not interested in that. And this, whatever, just an inference thing, fine. Someday we will. So we'll get there. And this is part of the philosophy that I bring, at least, which is doing really hard things takes time. And so you have to be careful. I think we learned that with Mojo 0.1. You have to be careful when you kind of declare success, because if people come in and it's not actually good, that's the impression that you'll make. And so we've been building in the open, and a lot of this stuff has been out there. But we even today, we're like, with y'all, we're sharing some of this stuff. But I think we'll make a lot more noise about this next year as well.
Nice.
Thank you. I lost track of the evolution of the license for Mojo and Max and the whole ecosystem. And I'm nearing to a point that I need to start having convincing answers about where the license is going to be in the future, right? I know it's a kind of an unfair question, but can you maybe share a little bit more how you would hope the license would unfold, because I know it's free. We have to tell you that we are using it, but there's also the idea that if you're using for inferences, there might be a charge later on or something like that. So something more about the license would be very helpful.
Yeah. So so you're saying like basically how does Modular make money?
Yeah.
So so we are building a managed cloud platform. If you have inference you want to manage, and like come let us know. But Mojo is roughly competing with Rust or CUDA or other free technologies. Max is competing with other free technologies. We want to be out there, right? And so the license is take it, use it, you can scale it arbitrarily on NVIDIA. We do ask you to tell us about it because we'd like to know about that and work with you and maybe do a joint blog post. If you would like to work with us, well, we have limited engineering, and so then we could talk about relationships and things like that. But no, you can take this and use it. And so this is all quite important. We do have other relationships and partnerships we'll be announcing next year, which are really cool too. And so there's more to come.
I have one question. Hi, my name is Dhruv. Great to connect again. And thank you for these meetups. It's such a great opportunity to be a part of this technology as you're building it. I'm coming from a physical AI context. I don't know if this question has already been asked. Would love to know if you're thinking about edge hardware or AIoT is the new word I'm hearing around this. I would love to hear your opinions on this. I'm Dhruv Didi. I'm founder of Solo Tech. Yeah, just interested in this.
So we have not announced anything with edge hardware, and I'm trying to keep the team focused. I would like to help the entire world, and so we'll have more to say about that next year. So, and it's very clear that Modular cannot do all of the hardware. So we'll get there. Yep. Thanks.
I had a project where I needed training, and I really liked being able to use Mojo for the kernel stuff. And I keep hearing this sentiment. There was some stable HLO OLR thing in Zig that says the same thing. Oh, we're just inference. And I'm at the point now where I have to make my own language because I don't understand why does no one want to support training? You say it's hard, but I don't understand what you mean when you say that.
Okay, you're on to me. It turns out that training is also matmals. Turns out that, again, we're arbitrarily general. It turns out that even though Modular, again, is underselling what we're doing, other people are using Max to do training. And so if you'd like to do training, go check out Nabla. It's a community project. It's super awesome. It does both Jack style and PyTorch style training using Max. Today, Nabla, N-A-B-L-A. And so you can also ask us later. And so, yeah, so turns out that, again, what we're trying to do is we're trying to set expectations. There's a lot of people that have been very excited about what we're doing. And then I make the mistake of saying, yeah, and we'll do training. And then people are saying today. I'm like, no, I can't. We need to get some other things first. But this is the great thing about a community, right? Is that Modular people don't have to do all the work, right? You can go build that. You can go work with Tillman and say, hey, how about this? And what about this? Or whatever your jam is, and go work on that. And it's just math, right? That's a beautiful thing. All right, how about I pass it to Ferris? And Ferris, would you like to dive quite a lot deeper into what is this thing and what's inside the nuclear reactor? Oops. All right, here you go. Green button. Got it.
All right. Good evening, everyone. Thank you for being here. My name is Ferris, and today I'll present to you this thing called the graph compiler. So, not working. Oops. Click twice. Okay, how do I go back? Red button? Yeah, okay. So, the agenda today, I'll present to you what the graph compiler is at a very high level, because I'm sure you're wondering, what's this graph compiler? Everything is graph in compilers, so why do we call it that way? And then I'll talk about extensibility, which is the cornerstone of what the graph compiler can do. Then the Mach dialect, which is what we use to do fusion in all types of optimizations. And then I'll show you how every single thing in Graph Compiler culminates into emitting Mojo. That's the Mojo codegen part. And then we'll end with a Q&A. And disclaimer, I'm sorry in advance. I'm about to effectively squeeze 3 or 4 years of work into what I effectively have like 15 minutes. And so that's almost impossible. So if you have questions, just talk to me at the end. All right, so Modular is doing AI inference, and it's distributed. And at the sort of core of it, there's this framework called Max. And inside Max, there's our beloved programming language, Mojo. And the graph compiler is this concentric red circle around Mojo. It's not Mojo. It uses Mojo, it ingests Mojo, and you'll see everything later, but it's not Mojo. And so in deep learning infra, when we say graph compiler, what we mean is this very high-level diagram. We mean that, at least for our graph compiler, we expect you to give it a deep learning graph. That's the model.mlir. It's based on MLIR. And as well as a bunch of, a package of kernels, essentially, written in Mojo. And the output of the graph compiler is this model.mef. MEF stands for modular executable format. And it's the executable we run on various hardware, depending on what you were compiling for. And so that's the high-level overview of what a graph compiler is supposed to do. So if you're in PyTorch, or if you use the graph API and you build your operators, what you'll get is this DAG of operators that we call a graph, and that's why it's called a graph compiler. And if we go by dialects, there are roughly 3 phases in Modular's graph compiler. The first one is RMO and Mo. Mo stands for modular operators, and R is for relaxed. It's the same thing as Mo, is just more relaxed around shapes, so you can do like implicit broadcasting when you add 2 tensors, for instance. And this is your typical high-level deep learning operator set. So here I have an example, very simple model. It supports dynamic shapes. Those are the N, M, and K letters you're seeing on the screen. And you have your matmols, your adds, your activations, typical stuff. You are probably familiar with this. And the design is very Risk-like. We have only 135 operators as of today. That's small, relatively speaking, if you compare to other graph compilers. Vertices are your operations, and the edges are just tensors. And we also support side effects, meaning like you can change like an input tensor. You don't have to like create a new one every time you run an op. And we do various optimizations at this level, like symbolic folding. We know what the ops are, and so we can fold them. We do shape inference, constant folding, and many more. I'm just summarizing the important ones here. The second phase is MOG. I'll talk about it more later, but at a high level, MOG stands for Modular Graph Generators. And what you were seeing on the previous slide, like the matmul, this is what it turns out to be in MOG when we lower it. It's a structured kernel representation. This is what we use to do lambda-based fusion. And it's destination passing style in the sense that you've probably written kernels in Mojo. And what I mean by DPS style is that you'll get the output as an argument to your kernel, as opposed to like returning something new. And this does the conversion inside the MOG kernel. And the various optimizations we do are element-wise fusion, prolog, eplog fusion, view fusion, small constant inlining, a few others, but those are the main ones. Last but not least, the last phase of the graph compiler is MGP. MGP stands for Modular Glue Primitives. These are the primitives that we use to interact with hardware, so allocating memory, executing stuff, working with shapes, and extracting information from different objects. And all of this culminates in emitting Mojo and then JIT compilation. Little note on JIT compilation. It's like ahead of time compilation in this graph compiler, but we call it JIT because the kernels that you wrote that I presented on that first simple diagram, they're not elaborated. It's Mojo like with parameters. They don't yet have a value. And then the graph compiler would take care of giving a value to all those parameters. And that's why we call it JIT. And the optimizations you find in this phase are sequence fusion, which is just inlining a bunch of kernels just to reduce interpreter overhead when you're going to finally run that graph of ops, memory planning, and thing I like to call runtime constant folding. So if you don't want to explode your compilation time, you're going to just move that bit of code into the init phase of the model. So you do it just once when you start up the model, and then you don't have to do it later. And so what I described so far is a very simple graph compiler. There are some cool things, right? But I omitted the most important part. I lied to you on purpose because I want to ask a question like, how do you design a graph compiler that's going to be resilient to this fast pace of change in this industry? Like every month, I think there's a new attention flavor. I can't keep track. I stopped reading papers. I just have like 20 tabs of papers I never read. You're probably experiencing the same. Every year there's a new hardware generation, then new instructions, and then you have to use those instructions because if you don't get peak performance is non-negotiable. So how do you design a graph compiler that's going to be able to give you performance, but also be resilient to change? Because if you commit to something and then things change, you're now back to square one. You have to redo things, and the more you build something, the harder it is to rebuild it, and so you get the point. So before I give you the answer, I'd like to model the deep learning optimization space here. It's a 1D spectrum. In reality, it should be like a hypercube of trade-offs, but I don't think we can visualize that, us humans. But so we'll stay with the 1D here. On the left or right-hand side, there's kernel-centric. If you're writing kernels, if you like CUDA, if you like Mojo kernels, that's the side of the spectrum. What's really great about writing kernels is that you can get all the performance you want. It's fast to compile because generally it's very close to what the hardware is going to do, so there's not so much a compiler could do. You get predictable behavior, especially, again, because the programming model is close to the hardware. It's fully extensible because it's just code. You can do whatever you want with it. And fully debuggable depending on what the vendor provides, obviously. But the biggest problem with just writing kernels is that you get low coverage. Every time there's something new, you have to write something for it. And so it doesn't really scale. But on the other side of the spectrum, you'll notice like they're just reversed. You have what I would call more like compiler-centric systems for doing AI in general, in AI infra. They typically provide you like what I call productive abstractions, like a DSL, or that API set that I showed you in Mo. That's a high-level abstraction that you can use to program your hardware, technically speaking. And the cool thing with that is you get high coverage, but then you get all these bad things. You get a lot of the time subpar performance if you just use those. Compilation time can be slow if there's like a search space. So think TVM, you can think about that. And TVM can lead to like hours or days of compilation time because you have to search that search space. And unpredictable behavior because, again, the more your programming model is far away from what the hardware does, then you can't really predict what it's going to do. It's a compiler. It's a black box from your perspective. And extensibility is restricted by what the programming model provides you. If you try to do something that goes outside the box, that's not going to work. Or sometimes it does, but you get bad UX. And the debugging is just not great because you're debugging like operators, but the hardware is running instructions. So how do you map the two? So if we look at that 1D spectrum, we can conclude that there's no finite operator set, DSL, or programming language or model that can reliably cater to all the needs of deep learning. What that means is that whatever point you picked on that spectrum, you're probably wrong. And that's the conclusion we had at Modular. And if we go back to the question, so, okay, I can't pick a point, so how do I design that graph compiler? How do I make it resilient to change if no matter where I go, I'm going to be wrong? And turns out the solution we found was you're going to hedge by investing in programmability and extensibility. What it means for Modular is 3 easy steps. The first one is our beloved Mojo programming language. We have a productive way of doing kernel writing. So what that means is Mojo, you've probably done C++ or other programming languages. You can compare them all you want, do the language wars, but we think that we built a programming language for AI, and it shows. Like what I'm showing here on the screen, there's a blog post on this if you want to read it. We managed to get, like in just 2 weeks, state-of-the-art performance on MI355, which is incredible. Like I've never seen something so fast from developers. Yes, we have excellent engineers. Yes, you need those experts, but you also need the tools. And that's the first step. Second step is you design your graph compiler as mostly kernel infrastructure. What that means is you're going to be writing kernels. And when you find a pattern, something where a graph compiler could help you, you push that feature in there. The graph compiler is kernel infrastructure, first and foremost. And the last step is when it's time to get out of the way, you do just that. Meaning if the expert wants to do something, they want to enable some feature in their kernel or something that your programming model doesn't allow, it has to be easy and doable. And that's what the third point is. And the summary of all these steps is that write kernels, find a pattern, put it in the graph compiler. That's what has been mostly our recipe. It's very pragmatic in that sense. And so practically what it means is extensibility. I said that's the solution. I'm going to present to you the two building blocks of extensibility in our graph compiler. The first one is MoCustom. If you're familiar with TableGen, this is the definition of the op, this thing, this weird language. And it's very high level. It's a knob that can take any operands, returns anything, can have arbitrary parameters. And this is how you do a custom op that's not in the OPI set, the Mo operator set. And it's very abstract, very opaque from the point of view of the graph compiler, at least initially. The second building block is Mo.opaque. So the same way MoCustom is like to kernels, Mo-opaque is to your arbitrary type. So your kernels don't have to just work on tensors. You can have your KV cache be a tensor, but it could be anything else. You could have I don't know, database handle in your kernel. You can do anything you want, and this is built into the graph compiler. And if we go back to the original diagram, because this is a first-class citizen extensibility, it means that you don't need to rebuild the graph compiler. You write your model, you put in custom ops and opaque, whatever you want in it, you just provide the kernel implementation. And then the JIT compilation that I talked about earlier is going to take care of specializing everything and actually compiling it to binary. But there's no like 30-page document that you have to follow to write custom kernels or anything like that. You just do it. These operations, from the point of view of the graph compiler, they're just ops, right? They could have any name, any semantics. It doesn't matter. The graph compiler is not going to touch them. And so in a way, it's like a side channel for you to do anything you want in Max. So if you've been following, I said you write your kernels in Mojo. This is the signature of the Mo-Matmul kernel. It's open source. You can go look it up. And then I said that it's going to look like this in the graph compiler. But how do you bridge the gap? Like this is Mojo. This is MLIR. You can find some things on both sides, but they're very different. How do I know that I can do fusion on Mo-Matmul and generate this structure here? And the cool thing about Max is that we have a vertical system. We can introspect Mojo. Mojo, like I show you example here, this is the implementation of MoAdd, literally. Again, I'm showing you real code. This is not pseudocode. And what you get at the bottom is the IR representing the code at the top. This is in the lit dialect. Mojo doesn't have an AST, parses directly into a dialect, and we can programmatically introspect this. And so I show you with the highlights here, you can know what it registers, what it is. In this case, it's an element-wise up, and the fact that it's adding two things. And then you get all of this in the IR, and you can reuse it. And that's how we build these structured kernels. And this is the MOG phase of the graph compiler that I promised I would talk about. The thing you're seeing here is the structured kernel of Mo-Matmul. And you can find in light blue, that's a lambda. That's what we use to do epilogue fusion. And so I'm not going to go back 2 slides because there's a delay, but you've seen the Matmul, it has output fusion enabled. And that's how we know that we're going to be able to do epilogue fusion. And here I'll show you like an actual end-to-end example. Remember the original graph I showed you? There's a Matmul, broadcast, an add, and an activation, which is ReLU in this case. This is everything fused into one singular kernel. So I'll just give you some time to stare at this. Obviously, you can rewind this on YouTube at some point. But our fusion is effectively lambda-based, and that's how we do it. So if you've been paying attention to this, MOG fuses operators not based on what they are, but how they're written, based on the signature of the Mojo kernel. So everything I just presented on MOG, but fusing things and looking at structured kernels, all of this works with custom ops as well. And this is thanks to having a vertical stack and having your own programming language, being able to introspect that and do whatever you want with it. And the last phase of the graph compiler is Mojo Code Gen. It's work in progress because we're hard at work on finishing this. We're near the end. Can't give you a date yet, but we're very close to releasing this. And what you get on the left-hand side, that's the fully fused structured kernel I showed you like 2 slides ago. And this is the generated Mojo. The graph compiler generates Mojo. And you can see the relation like it's almost 1-to-1. And this is something you can stare at, modify, debug, whatever you want. Even the MGP stuff I presented at the very beginning, remember, even that turns into Mojo. So you don't just stare at kernels, you can look at what the runtime is going to do and do whatever you want with that. And the cool thing with emitting Mojo, because recall, like you're writing your kernels in Mojo, you're giving that to the graph compiler, it's going to parse the Mojo, and then not the graph compiler itself, but it's going to get a parsed representation, it's going to introspect it, and it's going to emit it again. Everything is Mojo, and the great thing about this is Mojo is human friendly. You can read it, you can debug it, you can modify it, and if you can picture something, some optimization or anything done in the Mojo programming language, then it can be done, because we're not, like, the thing we emit is a general purpose programming language. Of course, we're constrained, like we're not going to do literally anything in the graph compiler, but we're not stopping ourselves by using a restrictive representation. What you're going to get at the end is Mojo, and that's what you give as well. So that's your degrees of freedom, so to speak. So that's what we have today. We have relatively basic fusions. We have partial Mojo Code Gen, almost done. But thanks to this sort of architecture, we're going to be able to do more fusion, mega kernel being the ultimate fusion, you could say. We're going to improve our kernel registration, do vertical debugging, because remember, yes, you have a programming language, you can put breakpoints, you can do stuff, add prints if you want to, but you're sometimes building the graph with the graph API, and that also has to be part of the debugging experience, because it's not just the programming language. And we're going to do just that. Also going to improve the readability. Like, I'm actually going to go back 2 slides or 3. You see, like, all the variables, it's obviously computer generated, but we're going to improve that, don't worry. And that's it. Questions?
This is awesome stuff, but where the bits hit the wire, I mean, in terms of your support in Apple Silicon, which is why I'm here. I'm really interested in that. Your support in the NVIDIA, Blackwell and AMD. So, how is it that is it the lowest common denominator to be able to have this, Mojo code that will run at the fastest on all of those different, GPUs? Like, do you maybe talk a little bit about, that magic that happens to be able to write once, run fast everywhere?
If you're referring to kernels, can't hide it. Like, we have to be aware of the target. Like, if you're doing matmols, you can get like maybe 50% of peak performance by writing just one type of kernel. But the way we do it to get state of the art, or sometimes even better than that, we have to be aware of the target. But the graph compiler, for the most part, which is what I presented, is hardware agnostic. GPUs and CPUs have similarities, and that's how we do fusion. Other more exotic hardware may not fit this model well, but of course, as I showed you, you can bypass that. But Mojo as a programming language makes it so easy to not just have a bunch of if statements, like, okay, if this hardware do this, if we have some, I'm not saying we don't, but a lot of code is shared, and the recipes for writing something like matmul are so similar, and Mojo is so easy to use that we're able to support them so quickly with very good performance.
Okay, so have I read right that you're actually beating CUDA on certain types of matmul operations? And that's kind of, I'm really impressed if that is actually the ground truth, and I'd actually like to know how you're able to beat,
I'm the wrong person to ask this. I'm a graph compiler engineer. We probably have kernel folks here, I'm not sure. Seems like Chris wants to say something.
Yeah, I mean, I'm also the wrong person. I am not a kernel expert, but first of all, you have to understand that all of these systems are very complicated. So if you take something like the cuDNN or cuBLAST matmuls, they have a mini compiler within them. right? Because you have to get, as Ferris is correctly saying, to get the peak performance, you not only have to know all the tricks, but you have to assemble them in the right way. You have to do specialization, you have to do unrolling, you have to do all this stuff. And so you can't just have like every shape permutation, every tall bit skinning, all the things in a statically compiled thing. And so we have smart people, but what we're doing is we're assembling the tricks in a way that we're getting better performance. Now, when we say we're beating Kublas on Matmul, it's not by 10x. It's like, 6 to 10% maybe, but that's still material. The most important thing is that we're not worse. And so I think Ferris, she did a great job of explaining TVM and XLA and a lot of the AI compilers. The key thing to know about what we've built is we're not an AI compiler. We're throwing that concept away. We want peak performance. We want the best. We want to assemble and integrate all this crazy ass technology these fine folks have been building into a novel system that allows you to get the best performance without having the lowest common denominator system that we've all seen. And that's the only way that we can push hardware forward. That's the only way we can get everything out of that next ASIC that is not actually an NVIDIA GPU or something. And that's the only way we can make progress as an industry, in our opinion. So.
This is a very rookie but nerdy question. I think I understand only 40 or 50% of your presentation, but when you generate Mojo code, Mojo is very powerful and an amazingly not common language, but it does have one particularity because it lacks garbage collect, etc., which is the control of the lifetime of the variables, like the copy semantics, like very well thought of. But when you're generating code, the concern is still there. So maybe you could speak about the techniques or whatever you use to ensure that the generated code is also generating the best lifetime for the variables, maybe extending them to reduce the opportunities to the allocation, or just banking on the eagerness to deallocate. I'm very curious how you control the generation time, the duration of the lifetime of the variables.
Okay, so the code that's emitted from the graph compiler, the Mojo code, is operating on very complex things. It doesn't use all of the Mojo language features. The reason we're emitting it is not because we need traits or anything like that. It's because something that's readable, it's better than giving like a binary or worse, like assembly, PTX or something like that, x86. It's readable. And for the most part, what the graph compiler is generating is like pointers, small static arrays. And so we're not exercising the lifetime feature of the Mojo programming language so much that it matters, especially in large models. Even if you deallocate something a little too late, that's not a problem. But the graph compiler is mostly manipulating like pointers or really register-based things like, I don't know, integers and basic structures that are register passable, if you're familiar with register passable. And so, boring answer, we're not doing very complex things. It's mostly to give something back to the user that they can understand and modify and play with.
I'm kind of curious where the graph compiler starts and ends. So like, how does it integrate into Mojo or Python? I'm kind of trying to place, because one of the big questions is like control flow through a graph. That's kind of a limitation of a lot of the modern like Python DSLs. So you have to use a while, but in a weird way. So where does graph compiler start versus just other Mojo code?
Right, good question. We support control flow, meaning our mo opy set has mo.if and mo.while, where we're not doing the sort of interpreter magic that PyTorch may be doing when it tries to find graph breaks and stuff like that. We have a way of building the graph you want to give to the graph compiler in something we call the Python API or graph API. That's going to change. I think we have maybe something to say about this. So I'll defer probably to my colleague's presentation, but it starts out in Python. You build your graph. It's very straightforward and no magic there because we're here for performance pragmatism. We don't want to have to play in an interpreter's bytecode to find where the graph starts and ends. So you will be explicitly building graphs.
Hi. So, part of my ignorance, I'm not sure I fully understood the presentation. But you did mention databases in there, and I'm kind of wondering, like, I'm getting the idea that this compiler is what it says it is. It's a graph compiler. Is it meant? Is one use case maybe you want to compile like something like differential data flow over like a distributed system, something along those lines? And then following from that, I'm kind of wondering, like, if you were to summarize in one sentence what the essence of the graph compiler is, like, what would you summarize that?
Right. So for now, the graph compiler is your typical deep learning graph compiler. It's going to ingest a bunch of custom ops, doesn't know what it is, not going to act on them except for fusion. But for the most part, it's interested in deep learning operator sets. So matmols, ReLU, add, and everything. The reason I mentioned databases is because right now, today, if you try to build a graph with like a database handle or something, you want to do something in custom up, you can do that. The graph compiler is not going to get in your way. But of course, as things will evolve, I can't promise or say anything really, but if we find a gap somewhere and we deem it valuable to have something dedicated for it, the same way we're doing it right now for deep learning, we could do that. But for the time being, you have your side channel, you can do whatever you want in custom ops.
So again, this is, so by the way, like the internals of graph compiler is not something a normal programmer is going to have to know. We just thought that talking about this would be interesting. But a lot of what we're doing with the graph compilers, we're really flipping traditional graph compilers on their head. And so if you ask, I mean, there's a whole category of graph compiler people that are compiler engineers that work on these things. Most graph compilers were designed to integrate TensorFlow or PyTorch or Onyx or things like this, try to lower them, try to get good performance. And so most people think about graph compilers as a way to get performance. Right? That's typically what people are. So Fusion is a way to get performance from operators. I think that's nonsense. So that's not what our graph compiler is about. Sorry, Ferris, I know you love performance. In today's world, if you want performance, you could just write CUDA kernels, right? Right, a massively hand-fused CUDA kernel and you get performance. And so there's no way that a graph compiler is going to give you better performance than writing all of the ideal custom CUDA kernels by hand. And so no, a graph compiler is not about performance. What a graph compiler is about productivity, it's about scalability, it's about extensibility, it's about new hardware. And so what the graph compiler does, the short version, is it's a total productivity, scalability, portability hack. Because as Ferris is saying, what we're doing is we're saying, like, look, no, we don't care about Onyx anymore. Like, Onyx is a good thing, and I mean, many people do care about Onyx. We're coming at it from like the speed of light of the hardware. And so if your output is highest performance, sure, you could write CUDA kernels, but nobody can afford to do that. Nobody can afford to rewrite them when a new chip comes out. And so instead, what you want is you want to get, for example, Fusion, because now you don't have to rewrite all the permutations of all the different operators. Like, this is huge. This is what allows Modular to move so fast. Like what Hassan and others are going to be talking about is, like, again, you don't have to write MLR, obviously, to use our stuff, right? You're just programming in Python. You have no idea there's a graph compiler underneath there, but it just means you get good performance and portability and all these other things we want. And so, again, this is like compilers at their best. Compilers at their best are things that you can ignore. You don't know that you have. The compilers that people notice are the compilers that are misbehaving and crashing and forcing you to read MLIR, or like looking at compiler internal dumps. Those are bad compilers. The good compilers are the ones that are making you happier, more productive, and that generally you don't have to know that it exists. Now, this approach is like so fundamentally different than what anybody else's experience has ever done before that it's like really crazy. And features, so full support for dynamic shapes, not just unknown dimensions, but fully parametric dimensions where we track symbolically the shapes. Like that's actually really fundamental. That's what enables next generation eager mode, right? These things are very nerdy. That's my cup of tea. But they're not things that people are forced to learn and use. It's the implementation details that come in the benefit of building this next generation stack. And so, you know, your question, I think the great question is like, how do you explain what the graph compiler is? It's productivity. It's about scalability. That's what the graph compiler does. And you know, ideally, unless you want to look at the generated Mojo code or something like this, ideally, you don't have to know it exists, which is also cool.
Any more questions? All right, I think that's the end for me. So now I'll give it to Mike. He's going to present to you that Python thing that I got questions about and how we're going to improve how you can build graphs and different decisions behind this and how it's going to be really.
Can you hear me well with the mic switch? Okay, great. If I can manage to hit the correct slide. Okay, there we go. So much for coming. My name is Ehsan. I'm a product manager here at Modular. I work on Max. Today, I would like to share more about the new API that we published. And I also have a notebook that I'm going to show you. But for a bit of context, so before 25.7, which was our previous release, our modeling API and Max API would look something like that. You can see some resemblance to PyTorch if you're familiar with like NN module, the way that you declare your model. But also you would have to write more, you would have to scaffold an extra graph and be more explicit about tensor input type and things like that. And finally, you will be able to compile and execute your graph. So what we have done for 25.7 release, we have introduced a new set of API. I'm going to also talk more about the API philosophy, but the core philosophy that we are after is we want to be more PyTorch-like. We want to have PyTorch-like abstractions, get good ideas, adopt good ideas, but also adopt them in a way that makes sense for us. So if I would just cover the perhaps the import layer, you would guess this is very similar to PyTorch or actually the PyTorch code. And that's the intent. You would exactly write the NN module, and then the only difference is there's a call function, and then normally you will be able to create an input, call your model, and also compile your model. I'm going to talk more about this thing. We have an eager mode, and technically it's a lazy evaluation with eager semantic because everything is graph-based. And finally, you can also have your model compiled. This is very similar to torch.compile concept, but completely different methodology. And we will, it uses our graph compiler and things like that. Now I need to switch my screen. Okay, there we go. Is this big enough for everybody? Okay, good. All right. So I've prepared an introductory tutorial, particularly for PyTorch users. And we're going to see it side by side examples of PyTorch code versus Max. This is going to be basic. And the code is also available in our Modular. If you go to Modular workshops, the code and the material should be under Modular to Mac December 2025. So the very first, yes.
Yeah, we're not getting it on the live stream.
Oh, sorry.
Do you mind doing some share real quick?
Yes.
Cool. Which one did you want to share?
This one.
That one? Okay. Cool.
Is it
you.
good?
Yep.
Okay, perfect. All right. So starting basics, how PyTorch does tensor creation has torch.tensor. You can pass it a list or a iterable, torch.zeros, things like that. Very familiar API. In Max, we also have a tensor. The only difference is we have a notion of constant tensor. And we also have zeros, ones, things like that. You can compare the outputs. But one thing you might notice is the default, which I'm going to talk later, is basically Torch assumes the default is float 32 CPU, even if you have GPU to be explicit. But in Max, if you have GPU, it automatically uses your GPU, and even the default is bfloat 16. So quickly, the key difference, generally, what I would like by the end of this talk for you to remember this conceptual model and dictionary to be able to translate your PyTorch code into Max. Next, yes, I talked about the defaults. You can see, you can print them. You can print the default D type and device. Next is about device management. So here is this familiar PyTorch code, checking if CUDA is available. If available, you do .CUDA. Here, we have a driver API. You can import CPU and accelerator, and you can also, let me show you the output. GPU is available, and as I said, by default, when you create your tensor, it automatically uses your GPU. Here, you can transfer it to CPU. Looks very familiar, and you can also get it back by being explicit to accelerator. Data types. Let's compare data types. So PyTorch has default tensor is float 32, or is bfloat 16. You can also set the default or the data type for your tensor, be explicit like this. We also have the context manager that you can include that will basically dictate the default data types for all the tensors that are created inside. You can also cast a tensor type to a different tensor type. And yeah, very, very simple and familiar stuff. Next is NumPy or PyTorch tensor interoperability. PyTorch and NumPy, well, you can translate between PyTorch and NumPy with the familiar from Python or from NumPy or NumPy.NumPy syntax. PyTorch relies on DLPack. We also use a DLPack, which is a data exchange format or protocol. So if you have a NumPy array, you can use tensor from DLPack. You'll get a max tensor. And also, if you have a max tensor, you can do NumPy from the LPAC. You get the tensor in NumPy, back in NumPy. Also, we can do this similar thing with PyTorch tensor. Here, for example, I have a tensor on my device, and I can simply call tensor from DLPAC. I don't need to move it to CPU or anything. That's the beauty of this data exchange format. And you will automatically get the correct data back or tensor back in Max. Next, we have the functional API. So we're going to compare PyTorch versus Max. PyTorch has this torch.nn.functional that you can call. It's a beautiful API. For example, you can calculate ReLU, JLU, all these things on a tensor. We also have exactly the same kind of API. You can see it matches. Similar thing with softmax, log softmax, things like that. Very similar. Matrix operations, matmols. You can create random tensors with torch.random. We have a dedicated random module, which in my opinion would make better sense. And the similar, or basically the same syntax as matmol. And well, I mean, one thing we need to work on is basically when you are printing or representing multi-dimensional tensor in a notebook or things like that, you want, better shapes here. Unfortunately, we are flatting. We need to fix this. Reduction. So you can do some mean, max, all the argmax, similar thing with max as well. We have for most of the, for the well-known reduction operations, we have the functional format, like f.max.sum, mean, things like that. For some of them, we also have the tensor format, similar to PyTorch. Here, for example, mean, max. So this is a dictionary or a comparison between API. Should be very similar. Perhaps the only difference here is with reshape. PyTorch has reshape, but also has view. We only have reshape. And also cast. So I briefly talked about random module. We can create random matrices. Same here. And now we're starting to get into more exciting stuff on module system. So PyTorch and then linear in Max. We can also import Max, or here we call it module v3, but we are going to, in the next release, we are going to actually drop it, and then everything will be max.nn. nn.linear. You can also call it exactly the same as you would call PyTorch linear model or any model. Embeddings, torch.nn embeddings, same argument. Here we have exactly the same type of argument. And now custom modules. So very basic MLP should look familiar. This is how PyTorch represents it. If you want to see the name, the parameters, max.nn is also very similar as I showed you previously. So the only difference here that you need to remember is we do not have a forward method. It's just a call that you need to implement. One thing that, I mean, is a nice utility for clean definition is we have a module data class, and actually, and then module is a data class that you can also wrap it like this, and it will turn your module. You don't need init or something like that. Sequential, very similar. And here I made a custom, let's say, Lambda module that I can use it inside my sequential and my Lambda. I'm using f.value. Example. Now, here I have taken a simplified version of GPT-2, I mean, GPT attention layer from Hugging Face. And I'm going to do some live coding. Yay. So what I'm going to do is I'm going to turn this live into a Mac code. So, and I'm going to do some mistakes. We'll see some errors, and then we'll be able to catch them and quickly be successful. So I'm going to, yeah, this is it. And let me also do this. OK. So the first thing is, I mean, first of all, as I told you, all of our NN modules is based on data class. We don't need to do inheritance. Here, we have the same concept, linear and then linear. We do not have forward method. We have call. One thing we do not have, or well, it's good to have, is the split method on a tensor. So we have it as f.split. You can. Let me also quickly show you everything that. If you go to our docs, for example, functional API, you can see all the API listed here. And also same thing for tensor and random. OK, that's a very quick reference check. I told you that we do not have view. We have reshape. So reshape. We have the same transpose. This should be easy. There's a mistake here. We're going to see the error, and we're going to fix it together. Let's do this. And there's also a mistake here. We're going to see the error. And I think that should be it. OK, let's run it. OK, the first thing is you see we do not have, I mean, dim. PyTorch uses dim. NumPy uses axis. We like NumPy in a tensor manipulation format. We are, I mean, leaning more towards NumPy. So the only thing I need to change is change this into axis. Same thing here. OK. And the second error is going to be about, oh, OK, split sizes. Yes, so I actually didn't include the tensor here. Correcting the split. Another thing, as I told you, is reshape. There's an error here. I need to just pass them all as, let's say, a list. And then we have, OK, the same reshape. These are small fixes. OK, there we go. We have turned the PyTorch code into Max. And it took us small time. And now we can continue with the full GPT-2 block. Let's go and uncomment the whole thing. Okay, you can see the parameters. I'm not going to run the model. I'm not going to run past these things. We have more content about tutorials, things like that, which my colleague Michael is going to show you. The next thing is about model compilation and optimization. So what we have here, I have a model that I built. We can pass it some random input. So this is an eager output. And later I'm going to compile my model. And then we're going to also see the compiled results. So as you can see, they match. One thing that I should highlight is the model type itself is a class that we define. And when we compile it, it becomes a function. Here is a very quick and dirty benchmarking for eager mode versus compile mode. Eager mode is very useful for debugging and development. And for production, you will get the benefit. You will get all the benefits of a graph compile when you do model.compile. So very quickly, sorry for the color mismatch. So the numbers do not really matter that much. The order matters here. You can see, for example, when you compile your model, it's about 1,000 times faster. So as a quick cheat sheet, torch.nn, max.nn, torch functional, max functional, the way that we define tensors, modules, the only thing that is different is call versus forward. Operations are the same, have the element of functional versus tensor-like. And for inference, PyTorch requires recall.val, for evaluation, no grad, do not compute the gradient, and also can compile your model and later. For us, we only need to call.compile. And as the last series of examples, I'm going to also show you some Mojo code, because to be complete, I'm going to show you how to write a custom ops and how to integrate it in this new API. So if you've never seen a Mojo code before, I mean, first of all, we have this fantastic Mojo Jupyter Magic. So you can import mojo.notebook. It activates the Mojo Magic for you. And I mean, here is basically a hello world in Mojo. Next, this is simple vector sum in Mojo. I am going to use our libraries that are available when you pip install Modular. So we have a concept of layout and layout tensor in Mojo. So this is a very simple vector sum of two layout tensors, x and y, and the output. So the way at runtime, I'm specifying, we have the keyword compile time, which basically does the computation at compile time, obviously. I'm defining n to be 5 as an example, layout, and I'm allocating, let's say, 5 float 32, and I'm passing the pointer, and I'm initializing my layout tensor. Same thing for x and y as an example. And I pass them into vector sum, and we can see the result. Next, is it similar GPU kernel? If you haven't coded any GPU, the only thing for now that's important is you can take the whole thing, you can paste it. And the fundamental idea behind GPU is replacing for loops with threads. So have a concept of global ID that's looking and where the thread is. And we are doing bounds checking and then doing the sum. For runtime on GPU, we need to do a little bit more. We have the concept of device context. So we're creating a buffer on host. We are filling them with, and also I need to mention that when you see NQ star, these are async functions. And then we create a layout tensor from the buffer. Same thing for X and Y, initialize them. We're compiling our kernel. And one that we have recently, actually, we have added is the ability to do type checking for modules, or the compiles. So here, NQ function check is doing the type checking. And we let the computation to happen and finally get the output. Or being able to print the output, we need to move the buffer into host and being able to access them. So in this example, as a continuation, I've taken my CPU kernel and my GPU kernel. And what I'm going to do is we have a concept of custom ops, which we're going to see. That means that it's going to, there's a struct in Mojo. You need to have a declarator called compiler register. And it's a struct that is going to encapsulate all of your kernels depending on the target. And we are going to see the examples for how to use it in Python. So here, if the target is CPU, I'm using my CPU kernel. If the target is GPU, same code that we saw before. Now, I also should, need to mention that for custom ops, we need to package. Mojo.package outputs ops. I can show you here, ops.mojo package that we are going to include in our custom op or a custom function. So if you remember, I talked about functional API. We have also the notion of f.custom that is going to use the same name as I registered for my custom op. And here we have, let's say, two inputs, X and Y. X is 10 tens, and Y is 10 ones. So it's adding them all up. So X and Y initially, they exist in CPU. So if I call my custom vector sum on X and Y, I'll get the CPU kernel called, and if I move them into accelerator GPU here, you will see that it automatically uses the GPU kernel, and here we have a unified way of using our custom ops on Mojo in Python. There's no build system involved. Imagine if you want to do the same thing in PyTorch or other frameworks, you would need to write C++ code, have your own build system, build it, maybe shared object, have a particular setup in Python, being able to load it, and then we'll be able. Here we have a very seamless setup. That's it. That's the end of the notebook. There is a lot that I haven't covered. How do you load a model into how do you load the weights of a model, things like that. that all of them are covered in our documentation. Please do check them out. We have a reference of GPT-OSS implementation. If you go to Modular Codebase or GitHub repository, under Max Pipelines Architecture, you will be able to see the GPT-OSS Module v3. You will be able to see the GPT-OSS, how we implemented it using this API. And all the details should be there. And my colleague is going to also talk about more educational content. So I'm done. I think we can do some Q&A. All good? Okay.
So I saw, a lot of it was FP32 and BF16. In a very specific case, like, with the latest Blackwells, they have FP4. So that just got me thinking, could you have just done an FP4 or is there support for that?
Yes. So what we are working is FP8 and also some FP4 kernels. Unfortunately, I do not have examples here, but we do support FP8 before, yes. Yes, I mean, so I should be careful. I don't think we have full support for FP4, but yes, we have some support for it.
Hey, Hassan, when rip the experimental off?
Yes. Okay. So in the next release, end of January, we are going to move all these API out of experimental. We wanted to be deliberate. We wanted to catch all the bugs. We want feedbacks from you. Let us know if there's any sharp edges, and we can fix them quickly.
Quick question about the API for small syntactic differences from PyTorch. So it's not uncommon, for example, for data frame libraries, like, from pandas to polars, people will try to preserve, the exact API to the greatest degree possible, just because, it's just quicker to transition. Why make any differences? I was just curious.
So your question is why?
Yeah. Why not just keep the API like as close as possible?
Right. So, for example, one major difference is between forward and call. I mean, Max is for now is all about inference. Cannot have. We can call it forward if if you would like to see. Different type of API. We should call it forward. Okay, that's a good. If you see the PyTorch implementation, basically forward calls the call. So PyTorch also has call, but it's not used for programming. Small differences, like you saw, maybe some APIs we do not have the tensor method. Maybe they exist in functional format yet. Let us know if you would like to be fixed. We would like to be as close to PyTorch as possible. But also, we have our own philosophy, for example, around dim versus access, things like that. These are small things. Let us know if you hate them. We can definitely do something about them. Yeah.
Sorry, son. You're totally right. Right. So you're both totally right. So where there's no good reason to deviate, we should be the same. So let's just forward. Seems fine. This is also why it's experimental still, and we'd love more feedback on more things that can be pulled together. But also there are intentional changes, defaulting to bfloat 16, for example. Right?
Exactly.
And so
defaults. Yes.
There are certain things that are intentional because we're learning and we want to actually be forward-looking, and it's a good opportunity to do that. But it's just like Mojo's relationship with Python.
Yes.
There are many things that we could have, air quote, fixed that are superficial with Python, but instead we should just embrace the standard and therefore make adoption easier and go like this. So +1, if you have suggestions, please let us know, and we'd love to pull those improvements in.
Earlier I was asking about like the control flow of the graph. I'm also curious about, it looked like there was some MLIR lowering. So I'm curious, in compiler mode kind of makes sense. You would trace that, but I'm curious how that works with the eager mode. And when it comes to like off registration, like what the relationship is between the graph compiler and what you just showed with eager.
So if I answer your question correctly, you are asking about the relationship between eager mode and compile mode from the graph compiler point of view?
Yeah, so is
Okay.
it like, for instance, it's unclear to me right now whether like what relation eager has with the graph compiler, but model.compiler, whatever the compile function is, there was a clear like, okay, obviously this is going to like map to some MLIR DSL and then lowered from there, but eager, it's not as clear to me.
I think this is something that I'm not an expert. Perhaps Phyllis or Chris can help answer the question about the differences between eager and compiled mode from graph compiler and MLIR.
So so we're intentionally making this similar to PyTorch. That's a strong goal, but we're coming at things from a different place, right? PyTorch started with training, started with eager mode, started playing through the frontier of PyTorch 1 of deciding that eager mode's a good thing and dynamism is all very important, and then discovered that accelerators keep getting faster and faster and faster. Now you get bottled on eager mode, right? And so then they've done a lot of things that are really innovative and really cool, like tracing Python bytecodes and Torch Dynamo and all kinds of wacky craziness, which is very impressive, but it also kind of makes PyTorch 2 unpredictable, and we start tracing Python code and trying to make dynamic Python code static. Some demos can work really well, but like it just becomes very frustrating. So what we've done is we've said, let's flip the narrative. Let's build in performance first framework. That's why Zasan kind of made fun of us at the beginning. He's like, yeah, well, if you looked at the graph API, it was very low level, it was very painful to use, but it was never the intent that would be the actual programming model for Max. Like this is also goes back to the question of why not talk about this earlier. It's like we're just building into the point where we're starting, and we're not quite there, but we're getting proud of what we're doing. And so you need graphs for performance, you need fancy graph compilers like Ferris is talking about, but then you start to say, okay, well, I don't want to be tracing Python and trying to extract things. Instead, what you do is you start from, cool, I can bring eager mode into the system. And so the short answer to your question is, like if you have an if statement, like one side will execute and we're not going to try to do heroics to parse it. We'll make it explicit. And so you do actually stage the if into the graph, and you can do that in these operators. But what we've seen with a lot of models is a lot of models are compositions of other people's work. And just like Asan is showing, you can compile the entire model, you can compile subgraphs. And so if you're building into other people's layers, like you can fuse it just the layer example, and you can have hybrid, eager, and compiled models. And this interplay is actually really nice. And so the one major thing aside from API polish, which we need to continue to do, is compile time. In the eager mode, compile time in the December release, November release, is really slow. So that gets fixed in January. And so we're really excited about that because then it's really interactive and it feels good like an eager mode is supposed to. But now, again, you get the full performance of graphs and they actually work well together. They use all the same operators, all the same custom ops, all the same thing. Like it's like the same thing designed together instead of being like the compiled mode is kind of a different ugly stepchild of the eager mode. And so that's where we're going.
Thank you.
So to directly answer your question, eager mode is eager mode in quotes. So we've done a clever thing. So all of our stuff is built on the same stack. So you see, you saw Ferris talking about the graph compiler. The graph compiler is built on Mojo because it generates the Mojo kernels you're specifying, fusing, and so forth. This new API that you see here is built on the API to the graph compiler. And what's going on behind the scenes for the eager mode is that it's materializing a graph at the point when you request a result. So it's eager in that you get the semantics of eager functionality, but you get all the capabilities of our graph compiler, and it's building on all of the same infrastructure that you see for everything else. It's just a different mode of interacting with it. It's like the semantics that you get versus like defining everything in advance. So
yeah. Technically, it's lazy eval with eager semantic. And then when you print or when you do dot item, it materializes. I'm not sure if we have differences. There might be some differences, or there might be some optimizations that are turned off for the performance because we want eager compilation to be as fast as possible. There might be, so we're working on it. But eventually, I think we will figure this out. Yeah.
Like Jack's eager mode, where it's like actually just on the fly trying to
yes.
So it sounds like you're sort of building eager semantic over the compiler. It's still
yeah, so definitely related to Jax. Jax has a problem, which is it's built on top of XLA. XLA is fully static shapes. And so every time you do something, it has to go recompile things and specialize, and you change your dimensions, and that's recompiling. And that's literally what the this year release is doing, which is why it's slow. So again, one of the cool things about y'all's smart people's work is that our graph compiler and our entire stack fully supports dynamic shapes. And so the January release, one of the cool things that it does, it says, okay, well, fusion is really important. Turns out, like, you don't want to do a matmul and then a ReLU, right? For example, but shape specialization is actually optional. Shape specialization doesn't affect your memory bandwidth. Shape specialization removes some, constants, and like it's actually not that big of an optimization. It's important for inference, but for eager mode, you don't need it. And so what we're doing in the January release, we're saying, cool, don't specialize on shapes. Just actually use the fully dynamic shape version, which is something that Jax can't do. And what it does is it gives you a fully predictable, fully in control system. And yeah, you can specialize if you'd like to, and you can have power user features, but your eager mode doesn't have to recompile everything because you're not specializing on stuff that you don't actually need for performance. And so this is why it's like this very unique blend, because again, like we're finally building high enough that we can actually surface the power, and the benefit is it's just easy. And so that's really the benefit.
That's the reason why I had to stop using Jax.
Yeah, the shape specialization stuff is why I had to move my project off of Jax. But I still needed the compiler for performance because running a for loop in Python is, I can't think of a slower out, but yeah, that makes a lot of sense.
All right. Yeah, thank you so much.
Hello again, all. I'm going to be brief because I don't really have another presentation. This is more of an invitation. You heard a lot from Chris about how we're developing a unified framework to build, optimize, and deploy AI workflows. You heard from Hassan. The new API that we have, the Eager Model API, allows for a really intuitive way to build models that's easy to debug. And what we want to do is we also want to make that simple platform really simple to learn. And so we're aiming to make the single best way to learn transformer architecture that you can find. And that's this book, Build an LLM from Scratch in Max. I developed this with a technical writer here at Modular, Patrick Bradford. And this is live now. You can go to llm.modular.com and see this tutorial. It will walk you through every step of developing the architecture of GPT-2 using the Max Eager Model API. And let me start with why we did this. We were really inspired by tutorials from Andrej Karpathy and by Sebastian Rasche on building GPT-2, on building an LLM from scratch. These are very popular, successful tutorials that help you learn the architecture of the now ubiquitous transformer architecture. However, we really wanted a tutorial that would walk people through how to build that architecture using the Max framework. And so the result is this tutorial you see here. There's 12 steps. You can kind of see the chapters on the left-hand sidebar there that walk you through causal masking, model configuration, layer normalization. I'll even show you one of the steps here, specifically how you do multi-head attention. You're familiar with the attention is all you need paper, then you need to implement multi-head attention in order to complete the GPT-2 architecture. And this book allows you to close it down. You can see steps in the text. You can see steps in comments. And you basically fill out these to-dos. And through these steps, you both learn how does this API work? What's the syntax? And how can I access the documentation and build something with this? But also, how does the transformer model work? And what were the architectural decisions that impact its performance? Additionally, all these steps are interactive. If you complete a few steps, then you can run tests and get feedback on what you did correctly or what you're missing. The idea is that you're not in the dark as you work through the various steps of this architecture. We really wanted to build on a popular series we have. If you're familiar with Modular's journey, you might know our GPU programming puzzles. I've heard from developers that they found it the best way to really understand GPU programming because it's hand-on, interactive, and really high feedback. And so we wanted to do the same thing for transformers. This is all live and open source now. The things that you'll learn transformer architecture, you'll learn why these architectural decisions matter, and you'll learn the Max framework. What's next for our tutorial? We are actively accepting community contributions. You can go flag an issue if something doesn't work as you expected. You can submit a pull request. We actually just merged our first community pull request this week. Someone saw an area of improvement, made the suggestion, and we implemented it. Things that are coming ahead, we will continue to improve compile times in the API as new API features. This is a rapidly changing API. As new features are developed, we will reflect that in the tutorial itself. You can also expect us to expand to additional model architectures. There's kind of a landmark architecture in GPT-2. You can learn a lot about transformers in a fairly accessible format by working through GPT-2, but there are other things like KV cache that you're going to want to learn at some point if you're doing model development. And so we plan to continue to expand this book, and then at some point allowing you to serve custom models and go through that whole process yourself. I encourage you, if you're interested in learning more about transformers, please do check out llm.modular.com. Come find me after this if you have questions about the tutorial. We really want this to be the best learning opportunity for you. With that, I will turn it to my colleague Connor to close us out.
All right. A big thank you, first of all, to all of our speakers, to Michael, to Hassan, to Ferris, to Chris. Thank you all for walking us through the Max framework tonight. You guys absolutely crushed it. Huge shout out to everyone who's asking questions too. It's just really fantastic to see the energy tonight. I'm Connor. I recently joined Modular to lead technical ecosystem, so I am literally week 2. So that's why they gave me the closing notes and not a full tech talk here. So I promise to keep this very brief. First off, we are still here for another hour, so feel free to hang out. We have dessert in the back now. There's still food. There's still drinks. We'd love to chat with you. If you have more questions, we would love for you to come talk with us about them. If you have ideas for what we should be building, not only should you come talk to us about them, but you have the opportunity to build them with us. Because if you're interested in getting more involved, whether that's contributing to Mojo, whether that's helping us build Max, or just staying in the loop, we would love to work with you. We have people who are already building off of Max. This is very real. There is much more coming on as soon in the new releases, but PRs are already being merged. We're adding to the language. Mojo 1.0 is coming even. Some of you may have heard of that. I know Chris is delighted to talk about that even more very soon, and we just published a great blog post that is a fantastic companion to everything we're talking about here at the Max framework. But we would just absolutely love for you to come build with us, and you can obviously join us in Discord, on our forum, and everywhere else. Those links are all over our website and at our /community page. And as I mentioned, we've got a lot coming 2026. We're going to do a Max hackathon even. We don't have an exact date for that yet, so stay tuned. You're all going to get an invite. Don't worry. We'll make sure of it. Probably February or March, though. And we want to give you the opportunity to get your hands on with this. But if you are ready to do it today, great. We have much of this on GitHub to work with you on it right now. And finally, I would love for you to help me with one more thing. So obviously the speakers here, huge shout out to y'all. But really this event would not be happening without both you and the community, but a lot of folks behind the scenes. We have Anara, we have Mike, we have Paige, we have Roxy, Courtney, Daniel, Jason, and too many more that I didn't name, and I apologize for that. So if you could join me in one more round of applause for everyone to help make this happen. Thank you all so much for joining us, for the excellent questions. We are so excited to build with you the rest of the year and in 2026. And yes, stick around for some more food and we'll answer your questions. Thanks so much.